Here's an example of path coordinates in class 4 in dynamics. I think I'm going to actually change the order of these. So because I just did an example that was much more complicated. This is a much simpler example than the other one. So this will be example 1 and the other one will be example 2. So at the end of the other video, you might hear me say, and now I'll do another example. But this is the one. I'm going to change the order in these. Okay, so we have, this is from Benson Tung's book, and it's problem 2.4.21. A car at point A is 100 meters away from point B. See, I always wondered like what direction he was going. Is he going up and to the right, or is he going down and to the left? What is the what is the front? I would think that was the front of the car. But anyway, it begins to accelerate from rest. Okay, and begins acceleration from rest. What constant speed increase is required for the total acceleration to be 8 meters per second squared when the car reaches B? So he must be driving upwards and to the right, but that looks like, maybe I'm thinking it looks like a PT Cruiser or something. I don't know. Why would or maybe it's, I don't know what kind of car would look like that. If you know, write something in the comments section. Yeah, that's what I like hearing from people. So anyway, okay, maybe if Benson Tung is out there, he could contact me, tell me. All right, so let's see. We want the total acceleration. Should give us a key here. That total acceleration means the magnitude, right? So his magnitude right there. So the magnitude is going to be 8 meters per second squared when it reaches B up here, right? And so he says it's 100 meters away. We have to interpret that as meaning the arc length is 100 meters. Okay, so he's moving to A to B by 100 meters. We want to know what constant speed increase. So we're talking about the tangential component of the acceleration right there. So that's how we're reading this thing. So one of the things that we know is he's traveling right here. We could pretend that he's like this is, we could kind of stretch it out and think of this as a straight line, right? As almost a coordinate, right? As a separate thing, not a separate thing. I'm trying to think of the ways. I say we treat the path like a one-dimensional problem for the tangential, right? So this is the path he's taking. It's 100 meters, and he's moving along right there. So he's starting from rest, and he's got a speed right here. So he's increasing the speed all the way along here. So what we do is we end up saying, and we know, because we know distance and we know velocities, we could use this right here. We could say the initial velocity plus 2 times the acceleration, and this will be the tangential acceleration, by the way, so I'll put a T right in there, and times our delta S, right, as he's moving along. And he starts from rest, so that makes it kind of easy, right? So that means that, and we know this distance, right, is 100 meters. So I went ahead and write the velocity. And I could even write the velocity of B, but that's just the velocity that we care about what's happening at B, so I'm not going to give any subscript. It's going to be the square root of 2 times 100, so it's just 200 times the tangential acceleration, right? Now we write out the acceleration. It's going to be equal to AT ET, right, plus V squared over rho En. So we still don't know what this velocity is, but we can stick this back into there. We could also so when we do that, we could get the tangential velocity. Yeah, there you go. So let's plug this guy in here, and well, we know the magnitude, right? So we could say this is equal to the square root of AT squared plus this part squared, right? So it goes, and I can go ahead and stick this in at the same time. So I'm going to be doing steps. So I'm squaring this. So that's just going to be 200 AT, right? Because if it was squared, I can get rid of the square root. And then divided by, and the rho, which we know to be somewhere here. Where did you go? Did they not tell us? Nope, there you go. 150. 150. And that's all squared right there, right? And we know that has to equal to 8. So we can go ahead and square 8 and make it 64, or yeah. So we can, inside this, we could collect on top of AT squared. So AT squared, and it's got this value, 200 divided by 150, but squared, but plus 1 right there, ends up 2.778, right? And that's going to equal 8 squared. And so what we end up finding is AT is equal to 4.800 meters per second squared. Trying to pick out something that was kind of a different problem. That it's a fairly easy problem. Maybe not so easy when you start looking at it and you start to read it, but once you're done looking at the thing, you go, oh, okay, that was easy. Unfortunately, there are a lot of dynamics problems are like that, where you have to, when you're looking at the problem, you're pulling your hair out and you're confusing yourself, and you're not sure which direction, how to start and what to do. What troubles most students is they'll start looking through the book or through the notes for which equation to use, and that's almost what I hear all the time. I didn't know which equation to use, and you need to start thinking of it as which concepts to apply. And certainly there are equations that go along with those concepts, but like when you read these word problems and go, the total acceleration being the magnitude would be some of the key that you would understand that. And then to just start putting down stuff that you know that this is an arc length, and the velocity is always tangent to the path, so it's going to be like across all the way along here. It's almost acting like kind of a straight line, right? We're really just thinking about what the straight line speed increasing is. So if it starts from rest and it gets to some speed here uniformly, then we can go ahead and use this velocity change and the distance in order to get our acceleration. And from that, we could see the other steps to get to the answer. But okay, so there's another one bites the dust.